So the food and fuels. Those of you that had chemistry 2 years ago, if you recall doing the food burning, like the food burning lab or whatever, those of you that had it last year, I did like some version of that, the at home version, which worked ish. Um, but that's like the kind of concept of relating um, foods and fuel and energy in the thermochemistry. So they start us off with the definition of food value, the energy released when 1 gram of a substance is burned. So typically your labels um, usually are either calories per gram or kilojoules per gram. Um, Now, one thing to remember, and I don't think I have it in front of me, but on your conversions, um, don't forget that there's a difference between capital C calorie and lowercase and lower C calorie. Okay. Oh well, it's on here in the notes though. So uh, calories, one nutritional calorie, in other words, the calorie you see like on the labels, the capital C calorie, is equal to 1,000 little c lowercase calories. Um, one big C calorie is equal to 1 kilocalorie with the lowercase c. Okay. Um, so it talks about like energy in our bodies coming from oxidation of carbohydrates and fats. You guys probably remember from biology, like converting glucose into energy, um, which it says ultimately it produces carbon dioxide, water, and energy. So if you think about that, it might seem kind of weird, but that's actually a combustion reaction in a way. If you think about the products, right? So here's the combustion of glucose, the delta H, the kilojoules um, for that reaction. Okay. Um, then they're giving another example of this tristerin, um, which is an example of a fat reacting. Okay, same type of concept though. You can see the balancing of it's a lot crazier, but all right. So then just give some other facts about fuels. They talk about some other fuels, fossil fuels, natural gas, petroleum. These are also hydrocarbons. So you can see like down here, CH4, it's methane, um, C2H6, C3H8, C4H10, different hydrocarbons found in natural gases. So they're just talking about different energy sources and hydrocarbons. Um, Coal contains high molecular weight compounds of carbon and hydrogen. In addition, compounds containing sulfur, oxygen, and nitrogen are present as impurities that form air pollutants when burned in air. So, like, when you think about combusting, um, if it were a perfect combustion equation, all you would get from it is carbon dioxide and water. But we know that's not true with things like some of these fossil fuels. So, what happens is in the substances, they have impurities in them that contain other elements as well. So like sulfur, nitrogen, oxygen, stuff like that. And then some of the byproducts of the combustion with those things in it are what leads to some of the different forms of air pollution and stuff like that. So they talk about syngas, synthetic gas, the gaseous mixture of hydrocarbons produced from coal by coal gasification. Again, just another sort of energy source thing. Um, then they talk about other energy sources, nuclear energy. So we talk about like nuclear power plants. It's energy released in splitting or fusion of nuclei of atoms, which contains a tremendous amount of energy when that happens, the nuclear reactions. Fossil fuels and nuclear energy are non-renewable sources of energy. Um, the nuclear energy one is interesting because it depends on where you look, whether that's considered non-renewable or not. I've seen it listed as a renewable source in other places. Um, I guess it just depends on how you look at it. Uh, you're not really going to use up all the um, resources that go into it, but it does produce waste and stuff, which is not like a hazardous waste, which is really not sustainable. But yeah,
Maybe they're taking into account like thorium fluoride reactors and potentially fusion reactors.
yeah, and I'm guessing too that it's like the byproduct stuff too, like because of the amount of like radioactive waste and produce and stuff. Like that's not really it's not really sustainable. Although like the reactions themselves, like some of the reactants, like you said, are also limited to depending on what they use, whether it's like uranium or thorium or um, I
Like
mean,
the old uranium reactors are pretty inefficient.
yeah, yep, and the
Some of the newer stuff is much better.
um, and it depends also on um, what was I gonna say? Oh, the it depends on the rarity, like the rarity of the and who controls it too. Sometimes, because like China has a lot of the rare earth metal. There's a lot of those are found in like northern China, Mongolia area and stuff like that too. So that can lead to like shortages too and things depending on what metal it is and things like that. Um, so I guess it just depends on how they're looking at it. But then they say renewable energy sources. Um, again, we don't really do too much in terms of renewable and not renewable here in chemistry. That's more of an environmental thing, but they do list some of those. So, all right, what do we sort of focus on in chemistry? Well, we look at um, fuel values and how we calculate them and some things like that. So, I would write these down. These are given fuel values, and sometimes they give them to you in the problem, but other times they just expect you to know them. The fuel value, and these are generic, obviously, but for fats, the fuel value is 38 kilojoules for every 1 gram of fat combusted. And protein and carbohydrates are essentially the same, 17 kilojoules for every 1 gram of either of those combusted. Okay. All right. So that stuff, everybody's okay on that? Makes sense? Questions? I want to make sure everybody has a chance to get that written down. All right. So let's look at the first example problem. Um, it's the page 194 one, the sample exercise, not the practice one. All right. So a 28-gram, 1 ounce serving of a popular breakfast cereal served with 120 milliliters of skim milk provides 8 grams of protein, 26 grams of carbohydrates, and 2 grams of fat. Using the average fuel values of these kinds of substances, estimate the energy value, caloric content of this serving. Okay, so um, now there's a couple of ways you can do this. I typically prefer so remember, we've got fuel values, we've got fats, and we've got proteins and carbs, right? Since protein and carbs are the exact same amount, the fuel value, I tend to prefer to combine those two things if they have both of them. So the first thing I would do here probably is I would combine um, the 8 gram of protein and the 26 grams of carbs into a total of 34 grams of a combination of protein and carbs. All right. Then all we need to do is we need to figure out how much energy is in each of these. Okay. So we're going to do, okay, so for the protein and carbs, we're going to do 34 grams. And our protein and carb amount is 1 gram for every 17 kilojoules, correct? So we're going to go 1 gram, 17 kilojoules. Okay. Everybody all right so far? Makes sense? Okay. Then, so this comes out to be, hold on, 578 kilojoules. I'm not going to do significant figures yet because I'm not done. So 578 kilojoules, that's from the protein and carbs. Now I'm going to use the fat. Okay, so 2 grams of fat. And I'm going to convert the fat, which is for every 1 gram of fat, there's 38 kilojoules. So that gives me a total of 76 kilojoules from fat, right? All right, now the total. So to get the total, I'm just going to add these together. And I get a total of 654. All right. Everybody okay so far? Now, it wants, it says it wants the energy value, the caloric content of the serving, which they've already given us. So what we want to do here is we're going to convert this into, so the first thing I'm going to do is I'm going to convert the 654 kilojoules into, actually, I'm going to convert this into calories. Now, whenever it says caloric content, it's talking about food. It typically means big C calories. Okay. If you did it in little c calories, as long as you had the labeling right and the conversion right, I probably wouldn't mark it wrong. But so this conversion, and you guys have this in that conversion sheet that I gave you with all the different like English and English metric conversions. It's on that sheet. But it's 4.184 kilojoules for every 1 big C calorie. Okay, and this is going to come out to 156.3. So significant figures. That's a good question because I'm not sure if they're considering those. I'm not sure if they're considering these like. These would be constants, I'm guessing, like given numbers. So it wouldn't be those. It'd be this, I guess. So it's basically 156 calories, or I guess if you're going maybe by the 28 grams, maybe like 160. I'd take either. So something like that. And that's okay, like because it says energy value, which is usually per gram, but they said energy value of this serving. So they want it per serving, which is what they gave us the numbers for already. Does that make sense? So if they wanted it per gram, what would you do? Would say it again? Yeah, just divide it by the number of grams they told you here. And then that would give you per gram, right? Yeah. No, not in this, because they've essentially told you that this serving contains, like, they've already given you, they've done whatever breakdown they need to between the two, and added it all together into this. So you would only have to do that if they broke it down separately or somehow gave you the data to like separate it out or something. So, all right. Second, part B. A person of average weight uses about 100 calories per mile when running or jogging. That seems so unfair. Like, a mile's a long distance. It should be more calories than that. Um, I guess. How many servings of this cereal provide the energy value requirements for running 3 miles? All right. So they told us we've got 100 calories per mile, right? We're looking for 3 mile. So basically, what we're asking is 3 miles needs how many servings of cereal to power it, right? So we've got 3 miles, and we know how many calories per. So what we're trying to figure out is how much energy it is, and then how many servings that is. Correct. So what I would do solving for this is I would start with the 3 miles. Okay. Then I would use this conversion here to convert from miles to calories. So they told us it's 100 calories for every 1 mile. I'm just using that as a conversion here. Everybody okay with that idea? Okay. Now, this is going to, so you could solve this, or we want to know how many servings, right? Well, we can do another conversion because we're looking for servings technically. We know from our part A that it is 156 or 160, whatever, so I'm going to use 156 calories per one serving. Everybody okay with where I'm getting the numbers from, why I'm setting it up the way I am? So if you think canceling, like the miles cancel, calories cancel, we're left with servings, which is what we want. And this is going to come out to be, I think it's like, let's see, 1 point, yeah. So it'd be like 1.92, and then your book does this on some of them. It says like you can't have so in like your book, it treats serving kind of like people. Like you can't have 1.92 people. They say you can't have like 1.92 servings when I guess, I mean, in reality, you could measure out like 0.92 of a serving, but they say you can only have like one serving, two serving, three. Like, so you would need a minimum, you would need 2 servings. All right. All right. How do we feel about that? Good. All right. Let's do the second one, the practice exercise. This is normally I don't do those as well, but these are a little different. Well, sort of. Part of it is, but so I think it's just good to practice here. So part A, dry red beans contain, and now they're giving us percentages: 62% carbohydrate, 22% protein, and 1.5% fat. All right. Now, if you add those up, and this is something that trips people up sometimes, it does not add 100% equal 100%, right? Any guesses why not? Yeah, good. There's other stuff in food, right? So if you've got a problem like this and they're giving the percentages and it doesn't add up to 100, don't freak out. That's realistic. Like, there's other substances in there that are not those things. So that's totally fine. So they give us the percentages, then they want us to estimate the fuel value of the beans, right? So Here's what we're going to do. We're going to take the percent now. I did not do this on this problem. You can, if you want, you can combine the carbs. Well, let me do that. I didn't do it on my original, but so 62% carbs plus the 22% protein. Because these have the same fuel value, we can combine those. So that's 84% carbs and protein, right? Okay. So what we're looking for, we're looking for fuel value, right? Now, if you remember from the notes, fuel value is the energy released when 1 gram of a substance is burned, correct? The energy released. So we're looking for something in like kilojoules or calories per gram. Everybody okay with that? Okay. So what we need to figure out is how much we have of this. So, okay, so if you think about this, 84%, so turn that into a decimal. So 0.84. So you take the percent as a decimal times the fuel value. So our fuel value for carbs and protein is what? 17, right? 17 kilojoules per gram. Okay. And we're going to add this to the one for fat. So fat is 1.5. So we turn fat into a decimal. So 0.015 times the fuel value for fat, 38 kilojoules per gram, right? Equals, I guess it would help if I, so it should be somewhere around, yeah. So significant figures, I did 2 from these, so it ends up being 15 kilojoules per gram. So all we're really doing is taking the percent of the percent of the substance that's each thing as a decimal times the fuel value, and then adding them together to get the total. Does that make sense, or everybody get on there? Yeah. Not unless they ask for it in that. I'm okay with you leaving it in kilojoules per gram, unless they specifically say like the caloric content or something. Yeah.
We multiplied it with the percentage, right?
Correct. Yes. Yep. All right. Let's see. Last one. During a very light activity, such as reading or watching television, the average adult uses about 7 kilojoules per minute. How many minutes of such activities can be sustained by the energy provided by a serving of chicken noodle soup containing 13 grams of protein, 15 grams of carbohydrates, and 5 grams of fat? All right. So for this one, we've got our light activity, right? 7 kilojoules per minute. We've got our chicken noodle soup, grams, proteins, and carbs. And we're looking for how many minutes of such activities, right? So if we look, we've got the rate of energy burn, I guess you would say, correct? And we've got the amount of energy per serving, really. Well, we've got the grams of each thing, and we need to figure out the amount of energy per serving, right? So what I would do, again, me being me, I would combine the protein, the protein, the carbohydrates. So that gives me 28 grams of the protein and the carbs. All right, then I'm going to convert this to, I need to know how much energy I'm getting here. So I'm going grams to kilojoules. So this kicks me off 476 kilojoules. And I'm going to do the same thing with my fat. 5 grams of fat is going to be 1 gram for, was it 38, right? Yeah. 38 kilojoules. And this is going to kick me off 190 kilojoules. Right now, adding these together comes out to 666 kilojoules. Now, this is the kilojoules per serving of chicken noodle soup, right? So we're okay on that. We don't need to do anything else and figure out anything special with this, but we've got to figure out how many minutes of light activity this will give us. So we're going to take the kilojoules now, and we're going to use this to convert from kilojoules to minutes of the activity. So kilojoules on the bottom because we're dimensional analysing it. Dimensional analysing, whatever. You know what I mean. Kilojoules per minute, and it's 7 kilojoules for every 1 minute of activity. So we're going to divide 666 by 7, and this kicks us out 95. It's actually 95.14. I think I just rounded to the nearest whole number. I don't know why I chose that. I don't know if any of these would be considered measurements or if they're all constant. So let's do 95. 95 minutes. So that's how many minutes of the light activity you could sustain.